In this video, I'm going to explain grouping of capacitors. The symbol of capacitor is like this. This is a capacitor of capacitance C. If it is a variable capacitor, the symbol for variable capacitor is like this. This is not variable capacitor. Okay. There are two kinds of grouping, series and parallel. First, let us discuss capacitors in series. Capacitor in series. Let us take three capacitors, three parallel plates capacitor, one having capacitance C1, write on this, C1, C2 and C3. We have C1, C2 and C3. They are connected to each other. A potential difference V is given across the series combination. V1 is for the potential difference between the two plates of capacitor C1. V2 is potential difference between these 2 points, and V3 is potential difference across capacitor C3. First of all, let us give plus Q on capacitor C1 on the left face of capacitor C1. It is Q, which will induce minus Q on this side, minus Q. This is plus Q, minus Q on the left face of capacitor C1, and plus this plus Q. This is also plus Q on C1. Okay, but this side is lower potential, so this positive charge will flow through the next plate of capacitor C2. So C1 supplies charge plus Q on the left face of C2. So it becomes Q again, plus Q, which in turn it induces minus Q on the left face of C2 and right face on C2. Then this plus Q again flows through the next capacitor. Here it is distributed on both sides. It is plus Q, and it induces minus Q on this side, minus Q, and this plus Q will go to the ground. This is negative terminal, so it is grounded, zero potential. This positive charge flows through the ground. V1 is the potential difference between these plates. V2 is potential difference between these plates. V3 potential difference between these two plates. Okay, so we have Q equals to CV. This formula. From this formula, we have C equals to Q by V. C1 will be Q1 by V1. Okay, like that. Oh no, we have V equals to V1 plus V2 plus V3. So C equals to Q equals to CV. V equals to Q by C. We have this formula. Now, we have Q1, sorry, V equals to V1 plus V2 plus V3. It is divided into three parts, and V1 is Q by C1, V2 is Q by C2, and V3 is Q by C3. We have Q by C1 plus Q by C2 plus Q by C3. Since we take the C as the effective capacitance of the three capacitors, this is the equivalent capacitance of the combination, and it is connected through V. Here the charge is Q, so we have V equals to Q by C. Q by C. V is also Q by C, then Q by C equals to Q, let us take Q as common, 1 by C1 plus 1 by C2 plus 1 by C3. We have 1 by C equals to 1 by C1 plus 1 by C2 plus 1 by C3. That is for three capacitors in series. This gives the relation of, or the expression of, effective capacitance of the three capacitors connected in series. Now let us go to parallel combination. Parallel. For parallel combination, we are going to connect the three capacitance, the capacitors, not capacitance, the three capacitors in parallel. Okay, and the combination is connected to potential difference V. C1, C2, and C3. Here, they do not get the same amount of charge. So Q1 will be, as Q is given to the charge, this will C1 will get Q1, this will get Q2, and this will get Q3, but the potential remains same. Here the charge on the total charge on the the combination is Q, so we can write Q equals to Q1 plus Q2 plus Q3. If we take these three as one, that is the effective capacitance. It is connected through potential difference V. This is Q and this will be C. Then Q equals to CV, this will be CV. C is the effective capacitance and V is the total potential. And Q1 will be CV, C1 V, because they get the same amount of potential. Q2 also C2V, Q3 also C3V, C1V plus C2V plus C3V. We have V C equals to, taking V as common and cancelling, C equals to C1 plus C2 plus C3. This is the expression for the resultant capacitance for the parallel combination of three capacitors, C1, C2, and C3. Thank you.